everyone. So today we are starting our chemistry A2 level chapter 21, which is the further aspects of equilibrium. Okay, so today all of my explanations will be directly focused from the chemistry course book. Okay, so look, our first content is the ionic product of water. Okay, so before going into further details of this chapter, let's learn some basic rules of this chapter. Okay, so first of all, please note this down, the facts. When anything undergoes a reversible ionic dissociation, for example, I am telling that AB is broken down to A plus and B minus. Look, so this compound has broken down into ions, which is the A plus and B minus, but this dissociation is a reversible dissociation. Now, when any reaction undergoes when any reaction follows a reversible pattern, you know that a state called dynamic equilibrium is reached when the amount or the rate of forward reaction will be equal to the rate of backward reaction. So what happens at that moment is that the amount of reactants and the amount of products, or the concentration of the reactants and the concentration of the product, does not change. Okay, so at that moment we have a ratio of the concentration of the product at the top. With third bracket we mean concentration. So concentration of product is at the top and concentration of the reactant is at the bottom. Okay, so this ratio is what we are calling it as the equilibrium constant. So when we are calling this ratio as the equilibrium constant, when the reversible reaction has reached the state of dynamic equilibrium. And what is dynamic equilibrium? The rate of forward reaction must be equal to the rate of the backward reaction. Okay, so now firstly, when any compound undergoes a reversible ionic dissociation, then it is considered that the amount of ions produced is extremely negligible. Okay, the amount of ions that are produced from the main compound is considered to be extremely negligible. That means if you consider the concentration of AB in comparison with concentration of A, this turns out to be AB. Okay, because the value of A is really very small. What I am talking about is that if you subtract just 1 from 10 to the power 24, the value would appear to be 10 to the power 24 almost, because in comparison to 10 to the power 24, 1 is extremely negligible. Okay, so the first law is that when any compound undergoes a reversible ionic dissociation, then the amount of dissociation is considered to be extremely negligible. Okay, please write it down. Let me explain it in another way. For example, A had an initial concentration of AB had an initial concentration of A, and X mole of AB had dissociated, producing X mole of A and X mole of B. Okay, so what would be the final result? The final result would be A minus X, since AB is being reacted and they were 0 0. So some amount of A and some amount of B are produced. So amount of A is X and amount of B is X. Now here, as the rule says that the amount of dissociation would be extremely negligible, so the value of x is much smaller than a. So a minus x will be approximately equal to a. Okay, so this is our law. So if any compound undergoes reversible ionic dissociation, then the amount of dissociation would be extremely negligible. All right? Okay. Now let's write an equilibrium constant for this equation. Okay. Okay. Let's write a general equilibrium constant equation. For example, we had AN and BM, and this breaks down into n number of n number of A positive, I'm just writing positive, okay, and m number of B negative. Okay, so what would be the equilibrium constant? So the equilibrium constant would be K is equal to concentration of A positive to the power n, because n moles of A are produced, okay, and concentration of B negative to the power m, okay, divided by concentration of A to the power n and B to the power m. Okay, so so this should be the general equation of equilibrium constant for whatever is present. Okay, and we can make it more in general, that we can, in case of this ionic equilibrium, we better write the equilibrium constant equation like this, that Kc is equal to concentration of n A, okay, no, not required. Okay. So let's learn up to that. The amount of dissociation would be extremely negligible if it's a reversible ionic dissociation. Okay, now let's look at the second theme, that in chemistry we have a concept of small p, and small p is a mathematical function which actually means negative logarithm whose base is 10. Okay, so that means when you are talking about pH, which you may have listened from your junior classes, pH actually means the concentration of H, which means negative logarithm with base 10, and concentration of H plus. Okay, so P in chemistry means minus log with base 10. Now if you do not have mathematics in your AS level or A2 level, or if you haven't done additional maths in your O level, for those students I am just giving some basics, that if Px means negative log with base 10 of x, then the value of x would be 10 to the power minus value of px. Okay, just keep in mind this thing. Okay, for example, if px equals to for example 10, and you are asked to find the value of x. So x will be equal to 10 to the power minus px, that means 10 to the power minus 10. Okay, so that's the thing, that's the main thing. Okay, so now let's start with what we are saying as the ionic product of water. Now what is the ionic product of water? So ionic product of water is simply the dissociation of water into ions. Okay. Oh, one more thing I have to tell you here is that in terms of writing equilibrium constants, if you find any liquid state, or if you find any gaseous state, or if you find any solid states, consider all their concentrations as 1. Okay, because we will here only deal with the concentration of the aqueous solids, or aqueous liquids. Okay, not those which are directly liquid or gases or solids. Okay, now let's look at the ionic product of water. Okay, so look here, water molecule has dissociated into ions. If this seems complicated to you, then look at this. Okay, water molecule has dissociated into H plus and OH minus ions, which is a reversible dissociation. All right, so the equilibrium constant of our equation would be Kc is equal to concentration of hydrogen ion into concentration of hydroxide ion. Why? Because they were the products. So products should sit at the top and the reactant should sit at the bottom. Okay, but look here, water is in liquid state. Just we have learned a few moments ago that any liquid, gaseous or solid state has to be considered that their concentration is 1. Okay, so we would consider the concentration of water to be 1. So our equation stands out to be like this, like Kc is equal to concentration of hydrogen ion into concentration of hydroxide ion divided by 1. So 1 is cancelled out. Okay, divided by 1. So divided by 1 gives the same result. So the whole thing is this that remains, and we are changing the symbol from Kc to Kw to signify that this constant came from the water dissociation, and we are calling this constant as the ionic product of water. Okay. Okay. So look, this is our final equation. Okay, for the ionic product of water, the Kw. Okay, pure water at 25 degrees Celsius has got the value of Kw fixed as 10 to the power minus 14. Okay, 10 to the power minus 14. Okay, now let's find the pH of the neutral water or distilled water. Okay, so here we go. We have Kw having the value of 10 to the power minus 14. Okay, so now if H2O undergoes reversible ionic dissociation, then it produces, it produces equal amount of hydrogen ion and hydroxide ion. Consider that amount of hydrogen ion is X, so amount of hydroxide ion would also be X. So what would be Kw? You know that a few moments ago we have studied that Kw is equal to concentration of hydrogen ion multiplied by concentration of hydroxide ion, and in this case we are considering both to be x. Okay. So Kw would be equal to x into x, which would give you x square. Okay. Now again, our experimental value shows that Kw must be equal to 10 to the power minus 14. So x square must be equal to 10 to the power minus 14, which means x must be equal to root over 10 to the power minus 14. That means 10 to the power minus 7. All right. So x means concentration of H plus, which is equal to 10 to the power minus 7. It also means concentration of OH minus, but we are focused on finding the pH only. Okay. So we would say that pH is equal to minus log. Remember, P means minus log with base 10. So pH equals to minus log with base 10, 10 to the power minus 7. Now use your calculator to evaluate this. This would give you 7. Okay, so distilled water or neutral water has got a pH of 7. So that's why we say that neutral solution has got a pH of 7. Okay, now this equation is not only important in finding the pH of water. Which equation I am talking about? I am talking about this equation. That this equation is, should I zoom it? Okay, I am zooming it. So this equation is not only important to find the pH of water, it is also important in terms of finding the pH of acids and alkalis, or acids and bases. Okay, how? Let's see. Okay, now let's go to the calculation of pH of acids and bases. Okay, just what I am going to tell, keep this in mind, that what is the definition of strong acid? Tell me. The definition of strong acid is that in strong acids, the acid completely dissociates into ions, isn't it? For example, HCl would be completely dissolved to give you H plus and Cl minus, and there is no reversible reaction in these cases. Okay. So if you have some strong acid like this HNCl, okay, strong acid like this HNCl, so sorry HNX, so this would give you n number of H plus, so this would give you n number of H plus and X negative, I am writing. Okay. So here, if the concentration of this acid is C, now for 1 you have N here. Okay. So for C you will have NC over here. Okay. So for strong acids, the concentration of H plus will be equal to NC, where C is the concentration of acid. Okay, C is the concentration of acid. Okay, but basically in most of the cases we use monoprotic acids or uni-dissociation of acids, because in most cases the double dissociation is no way a one-way reaction. Most of the time the single dissociation is the only one-way reaction. Okay, let me tell you why is this. Because consider sulfuric acid, which is H2SO4. Now if H2SO4 first time dissociates as H plus and HSO4, sorry, HSO4 minus. Now then HSO4 minus would tend to dissociate into H plus and SO4 2 minus, but in this case this dissociation is a reversible dissociation. Let me tell you why. Because this ion is already negative, so it would not want to dissociate to produce a more positive ion to that extent. Okay, all right. So that's why always the unit dissociations, the unit dissociations are the one way dissociation if there are any. Okay, so let's not make it complicated, let's make the situation more easier. Okay, we are considering a monoprotic acid which dissociates completely into ions producing H plus and X minus. So in this case, in case of strong acids, the concentration of acid will be equal to the concentration of hydrogen ions. Okay, so concentration of acid, if the concentration of acid is C, then concentration of H plus would also be C. Okay, now in case of strong alkalis, strong alkali means it will also dissociate completely into ions. So for example, let me tell you, if you are talking about sodium hydroxide, then sodium hydroxide would get broken to Na plus and OH minus. So if the concentration, okay, we write A here, and this sodium hydroxide is a base. So if the concentration of sodium hydroxide is Cb, then concentration of hydroxide would also be Cb. This is because it's a complete dissociation. Okay, but this would not be the case in case of weak bases or weak acids, because weak bases or weak acids, for example, if I say that this HX is a weak base, weak acid, sorry, then it would undergo a reversible dissociation producing H plus and X minus. Okay, so in these cases, if the concentration of acid provided is Ca, I am not going into detailed proving of the formula, just I am telling you that, okay, let me go. Let's write an equation of the equilibrium constant. We are writing Ka. A stands for acid dissociation. Okay, so let's go. Like in the top we will have the concentration of H plus and concentration of X minus, and at the bottom we will have the concentration of Hx. Okay, now remember that we have the mole ratio 1 and 1 and 1 over here. Okay, so whatever it is, the amount of H plus that we are going to get will be equal to the amount of X minus that we are going to get. Okay, so if you get the amount of H plus as X, then you will also get the amount of X minus as X. Okay, and the concentration of acid is Ca. So putting all these values together, okay, then putting all these values together, then Ka will be equal to X into X divided by Ca. So it turns out that X will be equal to root over Ka into Ca. Okay, so this is how it's going to work. Okay, Okay, so you can say that the concentration of H plus would be equal to root over Kasa. Okay, Kasa or Ka into Ca. Okay, so you might argue that after dissociation, after dissociation we should have subtracted x from here, but at the very first I have told you that in case of reversible ionic dissociation, the amount of dissociated product would be extremely negligible in comparison to the amount of reactant provided. So the value of x here is very very small compared to the value of Ca. So that's why Ca minus x would almost be equal to Ca. Okay. The same analogy would go for weak bases. We would say concentration of OH minus will be equal to root over Kb into Cb. Okay. So this is how we are going to find the concentration of H plus and OH minus in strong acids and in weak acids. Okay. So in case of strong acids and weak acids, the concentration of H plus and OH minus will directly be equal to the concentration of acids and alkalis provided. But in case of weak acids and weak bases, the concentration of H plus will be equal to root over Ka, or the acid dissociation constant, into Ca, or the concentration of acid provided. Okay. And concentration of OH minus will be equal to concentration of Kb into concentration of Cb. Okay. Now, how to find the pH? Okay. After you find the concentration of H, when you already have the value of concentration of H, so you can easily find pH, isn't it? pH is equal to minus log of the concentration of H plus. But how you will find the pH if the concentration of okay, so how you will find the pH of a base or an alkali? Okay, so how you are going to find the pH of an alkali is, for example, you already know the concentration of hydroxide ion. Okay, you know it, but look at the equation for the ionic product of water. If you do remember that this equation is Kw equals to concentration of hydroxide ion, hydrogen ion into concentration of the hydroxide ion, and this will be equal to 10 to the power minus 14. All right. Okay. So now let's see that if you know the concentration of hydroxide ion, then you might find the concentration of hydrogen ion by using this formula. Okay, 10 to the power minus 14. So you know the concentration of hydroxide ion, just find the concentration of hydrogen ion and put it in the equation of pH. Okay. Okay. So let's go into examples over here. Okay, so these are easy. Look at this one. Calculate the pH of sodium hydroxide of concentration 0.5 mole per t cube. Okay, so this is sodium hydroxide. It's a strong alkali, and its concentration is this. So the concentration of hydroxide ion will be equal to the concentration of the alkali. It is 0.05. But they asked you to find the pH, so you have to find the concentration of H first. Okay, and you know that concentration of H, that formula, concentration, I'm just writing H and OH. Concentration of H into concentration of OH equals to 10 to the power 10 to the power minus 14, isn't it? So use that here. So concentration of H plus into concentration of OH minus is equal to 10 to the power minus 14. So concentration of H plus would be 10 to the power minus 14 divided by 0.05. Okay. So from here you will get the concentration of H plus and put this in the equation of pH to find the final value of pH. Okay. Look at over here what they have done. Okay. Or there is another shortcut way which you can follow, is that using rigorous mathematical derivation, a formula can be proposed that pH plus pOH is equal to 14, and pOH, you know, will be equal to negative log or minus log of with base 10 of concentration of OH. Okay. So when you already know the concentration of OH, find pOH, okay, minus log with base 10 of the concentration of OH, and now put this value over here to find the pH. Okay. Now same goes for weak acids. Okay. Let me tell you. Oh, here they have told, okay, find the value of Ka. Let's do this example. Okay, so we know pH is equal to minus log with base 10 of concentration of H plus. Okay, and so what is the concentration of H plus? Just remember the logarithmic conversion that I have taught a few moments ago. Concentration of H plus would be 10 to the power minus pH. Okay, isn't it? 10 to the power minus pH. Okay, let me show it again first. The rule was that, if px is equal to minus log with base 10 of x, then x would be equal to 10 to the power minus px. So similarly, you have the value of pH over here. So first you need to find the H. Okay. So concentration of H plus would be equal to 10 to the power minus 2.9 as the value stated. So this would be 1.26 into 10 to the power minus 3. Now remember the relation between H plus and Ka. It was the concentration of H plus is equal to root over Ka into Ca. Now if you are to find the Ka, then square both sides to give concentration of H plus whole square. Okay, then I'm going from here to here. So Ka would be equal to concentration of H plus square divided by Ca. That means the concentration of the acid. And look at here, the concentration of the acid is already given. Okay, so concentration of the acid is already given, and H plus you have already found from here. You have already find out from here. Okay, so let's see. Now put all these values together to find the value of Ka. Okay, this is really very easy. Okay, so this is how we will calculate the pH of strong acids and weak acids, etc., etc. I would ask you to find to solve these questions. Okay. Now before going into the rest of the part, the acid base indicators, let's go into the part of buffer solution. Okay.